Right, we're going to be looking at rates of reaction in this session, and we're going to be looking at something called Maxwell-Boltzmann distribution. Okay? This is an incredibly important part of your understanding of how chemistry works. Okay, so you really need to pay attention to this. And those of you who have slept through the last session really need to pay attention to the podcast. So, we're going to talk about, first of all, do you know how energy changes during chemical reaction? You can get heat given out, exothermic, heat taken in, endothermic. The basic ideas of kinetic theory. This is that particles move around and they collide into each other. If you heat up a gas, what happens to the particles? They move faster. If you heat up a solid, what happens to the particles? They vibrate more. And catalysis is important. We know that? Okay. So, at AS, we just look at this in a qualitative way. That means we describe what happens. In A2, we look at this in a quantitative way, okay? And we look at the maths involved in describing what happens. Chemical kinetics is important because if you're in industry, you want to make a lot of product using as little effort as possible. In other words, speeding up the rate of reaction, okay? Optimizing the rate of reaction, all that kind of stuff is very, very important. And all of this comes out of collision theory. So, first of all, particles have to collide before they can react with each other. If all they do is dance around each other and never actually come into contact, then it's going to be no good whatsoever. Not all collisions lead to a reaction. Particles with energy can bounce off each other. Okay? They must have the minimum amount of energy to actually react. And that's called the activation energy. And finally, they must hit each other in a certain way. This is called a steric effect. So, you should know from GCSE that if you have more frequent collisions, okay, you get a faster rate of reaction. In fact, you should know from GCSE there are about 5 ways to speed up the rate of reaction. Just yell them out. What are they, please? Increase temperature, 1. Increase pressure, 1. Increase surface area, 1. Catalyst. Okay? Did we say increase concentration? No. Increase concentration. Thank you. So, if you have more frequent collisions, you increase the rate of reaction. But more importantly than that, if you have more frequent successful collisions, you increase the rate of reaction. And this is not just about getting the particles to collide more, this is about getting them to collide more successfully. Okay? Right. So, these are ways to increase the rate of reaction. This one doesn't work for all of them. Okay? There are some reactions that light plays a pivotal role, okay? But most of them it doesn't. So, increasing the surface area, okay? Break it up, break it into smaller pieces. You pause, please. Pause, please. If you have a large block and you cut it up into smaller pieces, you significantly increase the surface area. If a reaction it takes place between a fluid, so either a liquid or a gas, and a solid, you can increase the rate of reaction by having more sites the reaction can take place at. Okay? It can't react with the particles in the middle, so if you expose the particles in the middle, you can increase the rate of reaction. If you increase the temperature, then the particles move faster. But the much more important than that, if you increase the temperature, more particles have energy above the activation energy. Okay? If you increase the temperature, more particles have energy above the activation energy. With me so far? And if you have more particles with energy above the activation energy, you don't just get more collisions, you get more successful collisions. Because more of them have got sufficient energy to react. Whoa, we're not doing Zartman's experiment. Let's talk about this for a minute. In fact, let's not talk about that for a minute. Let's talk about something else for a minute. Shopping malls. Okay? Whenever I do this lesson, I always think about West Orchard Shopping Mall in Coventry. Okay? Not because it's a particularly great shopping mall, but because it's got 6 stories. And you can look down from the top and you can see all the people just milling about below. Okay? And what we're going to do for a moment is we're going to construct a bar chart. We're going to construct a bar chart of people and the speeds they're moving at. Okay? So to begin with, and I'm just going to have to use this table here, and it's going to hopefully not look too inelegant on the video. To begin with, you've got some elderly people moving around quite slowly. Okay? So we've got speed up here. Okay? There's my little bar chart for elderly people. Happy with that? Then we get all your regular people, they're walking around, okay? They're not rushing, they're not absolutely desperate to get anywhere particularly fast, they're just moving about. After that, you've got people, and these guys are on a bit of a mission, so they're walking pretty quickly, and there's their chart. You with me so far? And then finally, okay, present company accepted, you've got your sort of lunatic teenagers, okay, and these people, they're on rollerblades, okay, and that's their little bit there, okay. So what we've got is a shopping mall full of people. We've got elderly people or slow people, they're moving quite slowly, not much energy. We've got all your regular people just milling about, going from shop to shop, looking, seeing what they can see. You've got people, these guys, okay, they're ones that are rushing about. And then finally, you've got your people on rollerblades. With me so far? Yeah? And you end up with an energy distribution of people. Okay? Now, if you think about it, okay, it's all right, you can pan back now. If you think about it, you're walking through a shopping mall, minding your own business. Okay? Can we just pause, please? So what we have here is a distribution of speeds of different people moving around a shopping mall. And what could occur is if you're walking along, minding your own business, and you just sort of bump into somebody. Now, assuming, you know, that they don't pull out a knife and threaten to kill you, okay? You're walking along, you bump into somebody, what's going to happen?
Boom.
You sort of bump shoulders, oh, sorry, and you walk on, yes? And that's what happens when these two people here bump into each other. Got it? But what happens when you're walking along and Mr. Rollerblades comes tearing round the corner? Okay, you're just passing the little Thornton shop, you're going, oh, that's kind of nice, and then BAM! Okay, rollerblade kid bumps into you. Yeah? What's going to happen? You're going to fall over, yes?
Soon.
The point is that that speed means energy. Okay? And that if the particle's going fast enough, it's got enough energy to react. And so if you've got the rollerblade people, they've got enough energy to knock you over. Yeah? Everything to do with rates of reaction is about increasing the energy of the particles or making it easier for the particles to react. And everything we're going to do now, we're going to refer back to this model of sort of the shopping mall and the people bumping into each other. This is a Maxwell-Boltzmann distribution. And what it really is a bar chart in disguise. And it shows the distribution of energies. For the more mathematical amongst you, if you integrate the curve between any 2 points, you get the number of particles. For the less mathematical amongst you, the area under the curve is the number of particles. And what we're really saying is some particles have very little energy, a lot have got some energy, and a few have got loads and loads of energy. Now, on a point of information, when it comes to drawing these things, you draw them with a curve heading downwards but not crossing the axis. Okay? Not crossing the axis and not levelling out above the axis, as though it's going to hit the axis but stopping. So, and they show the distribution of energy. So some have got a little, some have got quite a bit, and some have got lots. With me so far? What we now need to consider is how changing something affects the shape of this. And in just the same way, we're going to think about how changing the shopping mall affects the number of people that are moving at different speeds. If you increase the temperature, you change the overall energy. Now, increasing the temperature, if I go back to my analogy, it's like setting the fire alarm off. Everybody starts going that bit quicker. Okay? Make sense? And it turns out that if you think about it, the slowest people are now going a bit quicker. The reasonably paced people are now going pretty fast. The people that were rushing around before are now tearing around. And the people on rollerblades, I mean, they're out of sight. Okay? So, and importantly, the peak shifts to the right and it gets lower. We get a greater spread of energy. Okay? 2 marks usually in an exam. Peak to the right and peak lower. Got it? Right. But the area under the curve stays constant. Why does the area under the curve stay constant? Don't have more particles. It's making sense, isn't it? Good. Again, okay, another temperature here. Okay, temperature 1 is higher than temperature 3. Okay, although the peak is lower, okay, the median energy, no, the median energy, sorry, the one with the most particles, that's the median, isn't it? The most single entries is the median? Yeah?
That's the mode.
The mode, the median's the one in the middle, and the mode's the most common one.
Yeah.
The mode, okay, energy is higher. Does that make sense? Okay? So therefore this temperature is higher. And then this temperature is higher. And the peaks flatten out, but the mode energy is the one, the energy that the most particles have, the most sort of single bit of energy. It doesn't really work like that, but you see what I'm getting at. This one here is further to the right. Peaks further to the right and it gets lower. Right. There is a line on these graphs that represents the activation energy. And if I go back to my badly drawn bar chart here, what we're really saying is that it's only the people with the skateboards that have got enough energy, or the rollerblades, to start knocking people over. And in just the same way, this is the activation energy, and these are the particles, important point, with energy above the activation energy. Got it? These are the particles with energy above the activation energy. So, when you increase the temperature, crucially, you significantly increase the number of particles with energy above the activation energy. Does that make sense? And it's reckoned, and it's a rule of thumb, that for every 10 degrees you increase the temperature, you double the rate of reaction. And if you think about it, you haven't made a huge difference to the overall shape of the thing, but you have significantly increased the area under the curve to the right-hand side of the activation energy. Got it? Therefore, you make a significant difference to the rate of reaction. So what on earth does a catalyst do? Well, your A-star GCSE answer was a catalyst lowers the activation energy. Yeah? Rubbish!
Pooned.
Catalyst does not lower the activation energy. It does not make it easier for two particles to react together. What a catalyst does is it provides an alternate pathway with a lower activation energy. So if we think about this reaction here, we've got a whacking great big activation energy, right? Or we could do it a different way. If we had a small activation energy to get to some intermediate, and then another activation energy, and so on, can you see that the total activation energy is now smaller? Yeah? And that's because it's gone a different way. It's like trying to drive from France to Italy. You can, should you want to, but you won't succeed, drive over Mont Blanc. Okay? Won't work, but you could try. Or, what's the smart option?
Fly.
Take the Mont Blanc tunnel if you're trying to drive.
Roly-poly.
Okay?
Roly-poly.
Does driving through the tunnel alter the height of the mountain? No. But it does provide a different route for doing the same thing, from getting from France to Italy. In just the same way, a catalyst provides a different way of doing the same reaction. Okay, and you'll talk more about it in Module 4. So, a catalyst provides an alternate pathway with a lower activation energy. Got it? And so now, look at that. More particles of energy above the activation energy. Going back to my analogy, adding a catalyst is like making the floor of a shopping mall slippery. It means lower energy collisions result in people falling over. It's not quite accurate, but you can see what I'm getting at. It means that particles that are moving less fast can still have successful collisions. Right. We're not doing that. We're not doing that. And we're going to look at why we use catalysts. Excuse me, please.
Sorry.
Catalysts reduce the amount of energy that you need to put in. Save energy, save the planet. Great. They don't just speed up reactions like by a factor of 1 or 2. The Haber process, okay, and you expect to know that iron is the catalyst of the Haber process, speeds up the rate of reaction by about 30,000. That means it gets as much produced in 1 second as it would take 8 months to do without a catalyst. That is a huge rate of reaction increase. Okay? You enable different reactions for use of better atom economy, enzymes, so on, and there we go. Catalytic converters, don't need to worry about that. So we're not going to do shining light. Increasing the pressure. Particles are closer together, they collide more often, and so on. Increasing concentration. There are more particles, and so it's easier for collisions to occur. Okay, you get more collisions occurring, more successful collisions, and so on. Okie dokie. If we think about a reaction, A plus 2B goes to C. To begin with, have you got any C? No. But you've got lots of A and you've got lots of B. The concentration of both A and B is going to decrease with time. The concentration of C is going to increase. As the concentrations of A and B decrease, what's going to happen to the rate of reaction? It's going to slow down, which is why the reactions to begin with will happen fast and then they'll slow down because the concentration decreases. Make sense? Okay. Measuring the rate. I'm not going to cover that. Measuring the volume of gas evolved. That's all the way back to GCSE, isn't it? Okay, you've got a reaction, measure the volume of gas given off at different periods, plot it in a curve, and you get a nice little rate of reaction graph. You could also measure the change in conductivity for some reactions. Or use a colorimeter to see when the reaction has occurred. Anyone done the disappearing cross experiment? Yeah? That's effectively colorimetry. When you can't see the cross anymore, reaction's finished. Okay. It's getting a little bit chatty now. What you can do is you can measure the rate, measure the initial rate using tangent to a curve. Okay? You should be familiar with this from GCSE maths. Everyone happy with how to do tangents from curves and so on? Yes? It's AS, is it?
Yeah.
Okay.
Food. Sorry.
Just going to be this little commentary on the video, you know, this voice just going poon every now and then. You're unlikely to have to do it. You should be aware the gradient is a measure of rate. Okay? Or if you differentiate concentration, you get rate. Okay, there's actually calculus in here. There's no calculus now in A-level chemistry, but in terms of those of you who are interested, there's a lot of sort of first year undergraduate chemistry, a lot of calculus starts appearing. So if you differentiate concentration, you get rate, or if you take the gradient and you measure the change in Y divided by the change in X, you can get the rate of reaction. Okay, though you're unlikely to be asked to do that. What we do look at, though, is the initial rate of reaction, and we will pick that up in Module 4. So initial rate of reaction, dearie me, which is that gradient there. Are we okay with that? Okay, if we can pause, please.